Thank you. So this is joint work with Anthony Leverrier from INRIA Paris and Gilles Zemmour from the Mathematical Institute of Bordeaux. And so in this talk, I want to present a construction of a family of error-correcting codes, which is homological. And by this, I mean that it's defined from a tessellation, so vertices, edges, and higher dimensional faces. It's log LDPC, meaning that the measurements act on a logarithmic number of qubits. And in the first part of the talk, we'll be mainly concerned with the three basic properties of an error-correcting code, NKD, number of physical qubits, number of logical qubits, minimum distance. So the original motivation of this construction comes from minimum distance goal. And it's actually started with this very simple observation that if we look at two-dimensional homological error-correcting codes, the most famous one is the Toric code, and it has minimum distance scaling like square root of n, number of physical qubits. And another quite famous family is the hyperbolic family, which has minimum distance scaling like a logarithm of the number of physical qubits. So it's quite natural to ask what happens with spherical geometry, since it's the opposite of hyperbolic geometry in terms of curvature. And then in the second part of the talk, it will be more concerned with local testability, which is a property of a code which roughly says that the distance of a state to the code space is essentially given by its syndrome. By essentially, I mean only for LDPC codes and also up to multiplicative constant. So this property was first defined in a classical setting, and it's been very useful for property testing, and it's been a tool in the proof of the PCP theorem. And in the quantum setting, it also has interesting relationships with single-shot error correction and large energy barriers. So after a short introduction, I'll give the construction. I'll insist on its minimum distance properties. And in the last part of the talk, I'll talk about the local testability. Okay, so just to illustrate the homological construction, I used the example of the Toric code. So in the Toric code, qubits correspond to edges, X measurements correspond to vertices, and Z measurements correspond to squares, faces. And this construction is quite general. It applies to any tessellation. It doesn't have to be squares. It applies to any dimension. It doesn't have to be two-dimensional like the torus. So it's a great way to come up with new construction of error-correcting codes. And now I want to insist on the geometrical interpretation of the three parameters n, k, and d. So let's start with k, the number of logical qubits. It's in a homological code, in a 2D homological code, it corresponds to the number of different loops that you can draw on the surface. So you can see here on the torus there are two different loops. This corresponds to 2 logical qubits. And if you want more logical qubits, you have to consider higher genus surfaces, and you get twice the genus as the number of logical qubits. But the geometrical interpretation also works for n and d. As long as you restrict yourself to tilings with tiles of area of the order of 1, then the number of edges of a two-dimensional code is going to be proportional to the number of tiles, so to its area. And you can think of the number of physical qubits as the area of the closed surface. And for the minimum distance, something similar happens. The minimum distance is the length of the shortest homologically non-trivial loop. So it's called the systole, and that means it's the length of the shortest loop. So that's something to keep in mind, because with this dictionary, we can immediately say that the Toric code here at the top is better in terms of minimum distance than this one at the bottom, because they both have roughly the same area, but the one at the top has a much larger systole. So with this dictionary, I want to say a bit more about the intuition that spherical geometry is something interesting to look at. And so we have to keep in mind the goal to minimize n, the number of physical qubits for a fixed minimum distance d. And with the dictionary, this means that we want to minimize the area for a fixed systole. And here on the drawing on the right, or here with the expansion on the left, you can see that in spherical geometry for a fixed radius, so think of it as a fixed systole, that means fixed minimum distance. The area is actually smaller in spherical geometry, and that means it will lead to less physical qubits. So there is a problem with this idea. There are actually two problems. The first one is that if you make a quantum code out of a tessellation of a sphere, you actually get 0 logical qubits. So that's not so good. And it comes from the fact that every loop on a sphere is actually the boundary of a two-dimensional region. So that means there is no logical qubit. And this problem can be fixed in the following manner. What we can do is quotient the sphere. So this gives us the real projective plane. And when I say quotient, I mean quotient by the antipodal map. So that means that our new topological space, each point of this new topological space corresponds to 2 points of the sphere, which are opposites. And if we do so, we do get 1 logical qubit. So that means the code is a little interesting. And we can verify that the computation that we did before works. So the systole of the real projective plane is pi. Its area is 2 pi. So we do get a systole which is larger than the square root of the area. So think of it as minimum distance could be larger than number of physical qubits. However, there is still a problem, and that is that to say that the number of physical qubits is the area of the surface, we have to keep tiles of area of the order of 1. And if we do this, we cannot construct an infinite family of codes because the sphere, which is the largest surface in spherical geometry, has finite area. And that's what makes it different from Euclidean plane, which is infinite, or hyperbolic plane, which is infinite. So as such, it's not possible to construct an infinite family of quantum codes. And the solution, well, a possibility is to increase the ambient dimension, so go away from dimension 2. And this is what we're going to do, but first we want to construct a quantum code. So we not only care about the topology, we actually want a discrete model of it to define stabilizers. We need vertices, edges, faces, and two faces and higher dimensional. And for this, we'll take a discrete model of the sphere, namely a cube. And we want actually a discrete model of the real projective plane, so we have to quotient by the antipodal map. Sorry? Oh, yeah. So in the question was, in the real projective plane, oh, sorry, where do I put the qubits? Well, here it's only to build up the intuition. I'm going to use directly the discrete model for the real projective plane, which comes from the cube. So it's coming in 1 or 2 slides. So here I don't really construct a code. It's coming next. So it's done here, actually. Once antipodal faces of the cube are identified, we can put the qubits on the edges of this discrete model of the real projective plane. And since there are 12 edges on the cube, this gives 6 qubits for this code. And we can now look at minimum distance. For the X stabilizer, it will correspond to the smallest homologically non-trivial loop. And on the whole cube, it's this red loop of 6 edges. So on the hemicube, once we quotient, it's made of 3 edges. And for the other side of the code, the one corresponding to Z stabilizers, we have to look at co-cycles. The smallest loop is given by these 4 red edges on the cube, so 2 on the hemicube, and that's why the minimum distance is 2. And we can make the observation here that the number of physical qubits of this code is the product of the minimum distance X and the minimum distance Z. So now let's see what happens when we increase the dimension. So we do the same. We start with a hypercube and we quotient by the antipodal map. And we did the computation to find out that we have these values for nk and d. And here we can make the same observation that n is still going to be the product of dx and dz. So that means that if we balance dx and dz, which is possible when we put qubits on p faces for this value of p. We get a minimum distance which is exactly square root of n, square root of the number of physical qubits. So that's kind of disappointing, but here we can see what lessons we take from this. So we compare the n-hypercube code family that we constructed with higher dimensional Toric codes. It does have an improvement on the minimum distance, but when we compare it with the usual two-dimensional Toric code, it's basically the same minimum distance, and also we had to pay a price for high dimension. That is that the measurement operators are now logarithmic. They act on a logarithmic number of qubits. So the analysis is that positive curvature does improve minimum distance, but high dimensionality brings it down, and overall we didn't win over the Toric code in terms of minimum distance. So that's not the end of the story, because we can look at other properties, not minimum distance, and the question is there a benefit of increasing the ambient dimension? And that leads us to the second property I was referring to, namely local testability. And so roughly speaking, this means that you can, if you have a code which is locally testable, you can distinguish between states that are in the code space and states that are far away from the code space only by looking at a few qubits. That means only by measuring a few checks. And that's a hint for single-shot error correction. For instance, in the quantum expander code family, which will be explained tomorrow morning in the plenary talk, they don't have local testability in terms of the definition I'm going to give in the next slide, but they do if you restrict to errors which are close to the code space. So that makes it a hint for single-shot error correction. And also, if you have LDPC code and local testability, this implies that the energy barrier scales like the minimum distance, which is interesting. So now I come to the formal definition of local testability. So the two quantities we want to relate are the weights of the syndrome and the distance to the code space. So we have to also take into account three normalizing constants, namely Q, M, and N. So M is here because otherwise we could artificially boost the soundness S, the local testability, only by duplicating some measurements, saying that we take it twice or more times. So we have to include this M here, not to have this possibility. N is only here because M usually scales linearly in N, so they balance each other. And Q is here because what we're interested in at the end is how many qubits we have to access to differentiate between code states and states that are far away from the code space. And Q relates the number of checks you have to look at and the number of qubits you have to address. So that's why we have to include it here. And the formal definition is here. We want Q to be constant and S to be constant to say that the code is locally testable. So in our case, we will have Q, which is logarithmic, so it's not going to be strictly local testability. So a bit of history. This notion was introduced by Lior Eldar and Dorit Aronoff in 2015. There was a construction by Matthew Hastings in 2017, which showed logarithmic weight measurements, which had a soundness scaling like 1/log to the third n, and 2 logical qubits. And there is a theoretical result by Lior Eldar and Aram Haro in 2017, showing that if we had a quantum locally testable code with linear minimum distance, so that's as we saw earlier, that's a heavy requirement. This would yield a proof of the NLTC conjecture, where NLTC means no low energy trivial state. Okay, so the M for an LDPC code, we can forget about Q, M, and N constant and really focus on the relation between the syndrome weight and the distance to the code. And if the code is only log LDPC, well, this affects the soundness here. So we lose a log factor in the soundness in this case. And what is interesting is that just like N, K, and D, there is a geometric interpretation of this notion of local testability, of soundness. And to see this, bear in mind that for a homological code, the syndrome corresponds to a boundary, and the distance to the code corresponds to the smallest filling of this boundary. So we can think of the soundness of a code as the constant we have to put to have a filling inequality. I hope with the drawing it will make things easier to understand. So I took an example here on the hypercube of dimension 4. In red, so here qubits are on two faces, measurements are on edges. And in this example, the syndrome is depicted by the red edges here. It's a boundary. And we have to find the smallest possible filling of it. And to have constant soundness, we would like that this filling is linear in the size of the syndrome, of the number of edges here. So we can use the following algorithm to find a small filling. Namely, try to define a partial filling, and by doing so, sending all the syndrome to the left part of the cube. So this will happen here in this case, and to do so we're only allowed to add some horizontal squares. And if we do this here, well, what we wanted happens, all the syndrome gets shifted to the left part of the hypercube. And we can repeat the operation to actually find a null syndrome. And if we come back to the beginning, we have a filling of our boundary of our syndrome. And this is an algorithm that is explained by Dotterer in his thesis from 2012. And to find the constant of Dotterer, you have to carefully choose the directions, the order of the direction in which you add some squares. So this is great because with this algorithm and the parameter regime we're interested in, we get a filling which is less than constant time the size of the boundary, which is exactly what we want for the soundness. But there is a problem still. We've been doing this on the hypercube, so that means topologically on a sphere, and a sphere has no logical qubit. So that's what I was saying. So now we have to shift to the hemicube, the real projective space. Topologically, this one has one logical qubit, but when we do so and we adapt Dotterer's algorithm, we end up losing a log factor here in the filling inequality. So the soundness we have is 1 over log squared. One of the log comes from the logarithmic weight of the measurement operators, and the other one from this log here that we lost. And this was kind of surprising to us because at first sight there is no reason why it would be harder to fill a boundary in the hemicube than in the total hypercube. But so far, well, we did not rule out that the real soundness is actually 1 over log, but so far we only have a proof for log squared. So before I conclude, I want to give a generalization of this construction. And this comes from the following observation that quotienting by the antipodal map to go from the hypercube to the hemicube amounts to quotienting by the repetition code. So to understand this, we need to have an algebraic model of the hypercube. I just took the Hamming cube here for the vertices, and by taking a 3-letter alphabet and saying that a star means any value between 0 and 1, we also have an algebraic description of higher dimensional faces. For instance, this edge here is 0, 0 star. And we see that the antipodal map is really translation by the all one bit word. And since the repetition code has only 2 code words, the all null bit word and the all one bit word, well, quotienting by the antipodal map really is quotienting by the repetition code. And this brings the following question: what happens if we quotient by other classical codes? So this is something we have investigated. And the good news is that this yields more logical qubits, more than 1. The hemicube had only 1 logical qubit. And we were able to compute the number of logical qubits and the minimum distances in this case when we quotient by another classical code. So if we choose the if we choose the parameters p, k, and d linearly in n, which is possible with the classical code, we end up with a quantum code which has a polynomial number of logical qubits and a minimum distance which is polynomial as well. So at first we thought we had a proof that this family of codes also have 1/polylog soundness, but actually there was a bug in the proof, and we're still trying to fix it. So as of today, it's only a conjecture. No, just for the soundness. So N, K, and D are proven, but the soundness is only a conjecture. As of
For every C? For every
yes. And with this, I want to conclude and say that we've been studying two properties of the h-hypercube code family, namely its minimum distance and its soundness. And what is new with the h-hypercube code is that it has positive curvature and it has high dimension. And yeah, my interpretation is that positive curvature does have a positive effect on minimum distance, but it is cancelled by the high dimension. And however, the high dimension has a positive effect on soundness, that is local testability. So the result is that we get state-of-the-art minimum distance, square root of n, and the record soundness 1/log squared of n. And with this, I thank you for your attention.
We have even more time for questions than we did with Elizabeth. So luckily, there's a lot of hands up. Okay.
The implications to NLTS at this point are none because of the distance being less than linear, right?
Yes.
So are there any prospects of using this idea of using quotient, whatever how you say it, with various C's to get better results on this front?
The short answer is I don't know. I guess as of today, no, because I think it's really needed to have linear distance in the proof that this would imply NLTC conjecture. So today, no.
Jonathan.
So I think I didn't understand. What's the problem with getting an infinite family of codes from the real projective plane by increasing the density of your tiling like you do with the Toric code?
Mm-hmm. So the problem is that so let me just go back. The problem is that here it is. If you want to have the interpretation that the area is proportional to the number of physical qubits, you need to keep tiles of area of the order of 1. And if you take smaller and smaller tiles in the sphere or in the real projective plane, you will lose this correspondence. Another way to see it is that sorry?
That's connected to the curvature. Is that what you mean, like with respect to the curvature?
So yeah, so exactly. If you want to keep tiles of area of the order of 1, you will have to inflate the sphere or the real projective plane, and then the curvature, which scales like 1 over the radius of the sphere, goes to 0, and you actually end up in a regime close to what you have in the Toric code. So you haven't really won anything.
Could you say a little more about this Doderer's algorithm? Like, does it work for more general complexes, or is it specific to the hypercube?
This one is really specific to the hypercube. In his thesis, Doderer also derives other algorithms for other complexes. But this one is really specific, and something that bothered us is that it's highly not symmetrical with respect to the antipodal map. So I'll just go back to the drawing. Here it is. It doesn't respect the symmetry of the antipodal map because it sends the syndrome all to the left, and then the syndrome, if we start with the symmetric syndrome with respect to the antipodal map, this syndrome stops being symmetric. So that's why you really cannot apply it directly to the h-hypercube.
Thanks.
Any further questions?
I'm sorry, could you just tell us what quotienting was?
In case of the HemiCube,
Oh, yeah, sure.
In homological code, you said that you have as many qubits as you have p faces for a given p, and now once you quotient by the antipodal map, you only have as many qubits as you have pair of p faces, where a pair of p faces are opposite to each other. So now you have as many qubits as pair of p faces, and as many checks as pair of p minus 1 faces for the x checks, and p plus 1 faces for the z checks.
Other questions? I have one, actually. Like, usually it's sort of obvious how to generalize results about codes to qubits. But here, I don't really understand what it seems like the fact that you have qubits is closely tied to the Hamming cube. Is it obvious to you how to generalize this to qubits?
Oh yes, you could just say that a p face is now a qubit, and that p minus 1 face is the corresponding x operator. You can generalize it the same way as usual.
The antipodal map, though, is exchanging code words of a repetition code on a...
No, this is not a problem, because this is just a map we're using to have another complex of 0 faces, 1 faces, 2 faces, and so on. And then it's really the same construction, the same homological construction as usual, so it doesn't interfere.
Any further questions?
Have you thought about what resources you'd need to have to realize these codes in a lab? Can you do it in 2 dimensions, 3 dimensions, 4 dimensions?
No, you can't. No, that's a problem. So the problem also is that since the weight of the measurement scales logarithmically, that means that if you want a large number of physical qubits, you have measurements that act on large number of qubits, and that's also not very practical. And you definitely cannot embed it, well, project it down to 2 dimensions. It's naturally high dimensional.
Any other questions? We're all questioned out. I got one more.
You started the talk by talking about Toric codes. So this is, to clarify, this is not quite a Toric code on RP2 because of the way the stabilizers are constructed?
Yes, the operators are not the ones of the Toric code. Yeah.
Okay.
But it's constructed the same way by identifying p faces with qubits, and measurements with x measurements with p minus 1 faces, and z measurements with p plus 1 faces. So in this viewpoint, it's a generalization of the Toric code.
Okay, thank you.
Okay, last chance for a question. Anyone? Bueller? Okay, let's thank the speaker again.